Hello, everyone. My name is Jimmy Fox from the University of Kentucky, and today I'm going to be talking to you about climate change impacts on precipitation and flooding in Kentucky. There again, climate change impacts on precipitation and flooding in Kentucky. This is work that I've carried out with Nabil Al-Armory here at University of Kentucky. And so Kentucky is expected to see increased average annual precipitation in 2055. Over the next 30 years, Kentucky is expected to see increased frequency and magnitude of extreme flooding in streams by 2055. And this is based on evidence reported by the United States National Climate Assessment, as well as work done by our group. So, future extreme flooding. Future flooding remains a concern for loss of life and destruction of infrastructure near streams and rivers. And so here we see a couple photographs, one in Johnson County, Kentucky, another in Scott County, Kentucky, showing a flood event in a stream. And so here on the left in eastern Kentucky, in Johnson County, we see a mobile home that's been destroyed by this flood event and is being carried downstream. On the right-hand side, we see a flood event in Scott County. That's my home county. And we see the inundation by the water flooding the vegetation in this image. And these images have just become more and more frequent, it seems like, in the news as we see these flood events occurring across Kentucky and across the United States. And so when we think about future increases in precipitation flooding, why will future precipitation and flooding increase in Kentucky? A few reasons. So Kentucky's projected increases in precipitation results from number one, higher moisture in the atmosphere due to warmer atmospheric temperatures, and number two, the expansion of the high subtropical belt within global circulation. And so let's focus on higher moisture in the atmosphere due to warmer atmospheric temperatures. And so first we can think about the greenhouse effect. And so higher moisture is a result there again of these warmer atmospheric temperatures. The climate is warming as carbon dioxide concentration increases in the atmosphere. The greenhouse effect is exacerbated. And so here we show energy from the sun that's warming the earth. Then some of the heat that is emitted escapes back into space, while other is held in the atmosphere due to the greenhouse gases, the gases that trap that heat in the atmosphere, with carbon dioxide being a primary cause. And so carbon dioxide gas as a greenhouse gas, the CO2 concentration increased by about 35% over the past 60 years. And so here in this graph, on the x-axis, we see a timeline from 1960 to 2030. On the y-axis, we see the amount of carbon dioxide as concentration of parts per million in the atmosphere. We see an increase on the order of 315 parts per million to 425 parts per million over this 60-year period. And then at the same time, we see a temperature increase by about 2 degrees Celsius over the past 60 years. And so in this graph, we have a timeline. This timeline is extending all the way from 1895 to the present day. And on the y-axis, we see a temperature change. And here, starting about 1960, we see this fairly linear increase in temperature, surface temperature of the United States. We see about a 2 degrees shift in the temperature. Higher moisture in Kentucky's warmer atmosphere is expected in the future. So as the greenhouse effect warms the air, the vapor pressure of water also is expected to increase. Therefore, water vaporizes more easily in warmer air, and the atmosphere is able to hold more water. This is especially meaningful in the humid climate such as Kentucky. And so there again, this increased water vapor in the atmosphere provides a source of increased precipitation as Kentucky's climate warms. Warm air can hold more water. And we see this, we see warmer air holding more precipitable water in this map of the globe. And so here we see a map of globally precipitable water that's increasing in the atmosphere by by a percent of 2% per decade. This is coming from NASA data. And so here we see at the near the equator, we see about a 70 millimeter holding capacity of the atmosphere, precipitable water of a depth of 70 millimeters around the equator, while when you extend towards the poles, you have about 10 millimeters of water that's held in the atmosphere. So there again, we see this warm equator air holding more water, about 7 times as much water being held in the atmosphere. Now, if we think about changes to the climate, we see that higher moisture in a warmer atmosphere occurred historically over the past 80 years. So here on the left-hand side, we see the annual winter and summer temperatures on average, and we see their changes. We see their percent changes, or rather their temperature changes in degrees Fahrenheit. And on the right-hand side, we see the annual winter and summer precipitation. Okay, and so essentially, these red hot areas on the left are showing an increase in the temperature of the atmosphere, and then on the right-hand side, these green splotches in the eastern United States are showing on the order of 10 to 15% increase in the amount of precipitation that's occurring. We can then project this moisture into the future when we think about a warmer atmosphere. And so this map shows the changes that occur to average annual precipitation when we have a warming temperature of the atmosphere. And so here we see from left to right in the top pane a 1.5 and 2 degrees Celsius increases. And as we have these increases in temperature, we see in the southern and southwestern United States, we see actually decreases in precipitation, while in the northern United States and eastern United States, these green areas are showing average annual increases in precipitation. Okay, but there's even more to the story because the wettest times of the year are projected to get wetter, and the wettest days of the year are expected to get wetter. And so this is going to provide larger flood magnitudes. We can start to think about this. The National Climate Assessment overwhelmingly projects that Kentucky will see wetter springs and winter. So here in the upper left, we can zoom in on Kentucky. We can see Kentucky here, the green area in the winter. On the right, we can see the green area of Kentucky in the springtime. And during these times of the year, we see anywhere from 10 to 20% increase in precipitation in Kentucky. And so now we're starting to think about the wet winter and the wet springtime being even wetter. And so this brings us to really our second reason for Kentucky's projected increases in precipitation. And so we see another reason is the expansion of the high subtropical belt within global circulation. Expansion of the subtropical belt. So the changes in the subtropical belt or its expansion affect where and when that precipitation will occur. Due to this expansion, the dry areas of the world may experience drier conditions during dry times, and the wet areas may suffer from precipitation falling in heavier, more extreme events during wet times. And so how does this work? So often what will be used to explain the expansion of the subtropical belt is really a 3-cell model for the globe. And so the way this works, we see a depiction of the globe on the right-hand side. The sun heats the equator more than any other zone. And so the heat is focused on the equatorial region. And then the Earth's surface in turn heats up that air. The heated, humid air rises, forming a low pressure system called an equatorial low. While rising, the air condenses and forms huge clouds and thunderstorms, which release a vast amount of latent heat. Okay, as that warm air continues rising and its temperature drops until it reaches a point where it cannot rise any higher at the tropopause, at that boundary, and then that air starts to move towards the poles. While moving from the tropics, the air constantly cools down and converges when approaching these mid-latitude regions, these 30-degree mid-latitude region. The convergence of air at the mid-latitudes increases the air mass and thus increases the pressure of the system. So we get this high pressure system that pushes atmospheric moisture further towards the poles. So essentially, this horse latitude or 30-degree latitude, mid-latitude system is a high pressure system that's pushing moisture towards the poles. In summary, the expansion of the subtropical belt, CO2 increased concentration warms the atmosphere. This additional warming of the air above the subtropical belt expands the air mass, increases the surface temperature, and increases the pressure, and causes the belt to expand even more and push moisture towards the poles. And this is really what we're seeing, in the seasonal map of changes when we were focusing here on Kentucky. Here we're looking at North America. Essentially, we see this increase in precipitation as uh, uh, as the mid latitude high pressure system is pushing that moisture further towards Canada. In the southern half of North America, we see these drier conditions, these net negative conditions in terms of precipitation change, while in the northern portion of the country, especially in the winter and spring, and in Canada, we see this net positive precipitation change, the increase in precipitation. So now we're understanding why Kentucky is expected to see increases in precipitation and flooding. How can we predict future flooding increases in Kentucky becomes our next question. Global climate models provide a means to do so. So global climate models can be used to predict how temperature changes impact future precipitation via increased moisture and changes in this atmospheric circulation that we were talking about. Results of global climate models can then be input to hydrologic models to predict stream flow, so long as we can account for all the uncertainty associated with these projections. Global climate modeling. And so, what is this global climate modeling? Basically, it's a fluid mechanics and thermodynamic modeling of the atmosphere. The global model is broken into grid cells. They tend to be on the order of 300 by 300 square kilometer grid cells that extend vertically into the atmosphere. Okay, and so for each one of these grid cells, the model simulates exchanges between both the ocean and the land masses through the hydrologic cycling. And then within the atmospheric portion of the model, the global climate models are simulating the fluid mechanics and thermodynamics equations, the governing equations for fluid flow and heat transfer within the atmosphere, and they're projected 100 years forward into the future. And so use of global climate models for predicting future stream flow, well, this requires quite a bit of work, quite a bit of uncertainty analysis, as well as downscaling methods. And so essentially what is done is assumptions are made about future greenhouse gas emissions and global warming. And so this requires assumptions as well as scenarios as to how land uses will change into the future and how fossil fuel emissions may change in the future, and a whole suite of high, medium, low conditions and scenarios are run for these future emission scenarios. These inputs are simulated within the global climate modeling that we just talked about, and then either statistical methods or regional climate modeling is used in order to downscale these simulations from those 300 by 300 square kilometers to closer to 10 by 10 square kilometers. This information from the statistical or regional downscaling methods is then input to hydrologic watershed scale modeling, where we can do stream flow projections. And so now we want to look at a case study for flood projections in the South Elkhorn Creek, which is located in Lexington, Kentucky. And so here again, we see a map of the United States, and then we can focus on Kentucky. So we see the state of Kentucky. Within the state of Kentucky, we see the Kentucky River Basin. And then here in the center of the Kentucky River Basin is South Elkhorn Creek. South Elkhorn Creek drains a portion of southwestern Lexington, Kentucky. And so this is a 60 square kilometer watershed in the Lexington area. It drains urban and suburban Lexington, as well as horse pasture, which we see in the yellow within this watershed figure. And so here is our method, a little overview of our method in order to project flooding for the South Elkhorn Creek. Again, we move through these steps of future greenhouse emissions within global climate models, and then downscaling via regional, that is dynamic downscaling method, and statistical methods. And then we ran that information, those outputs through hydrologic models. And so here's just a concept model view of the steps that are undertaken within this type of work, the steps that we undertook. And so there again, we have a set of different future emission scenarios that are run within a number of different global climate models, 15 different global climate models that then the results are then simulated through statistical and dynamical downscaling approaches via regional climate modeling. We then do a number of different bias correction techniques in order to correct the forecast data based on hindcast observations and hindcast modeling. And the output from this modeling provides us with precipitation data, temperature data, relative humidity, solar radiation, and wind speed. This information is then input to our hydrologic watershed scale modeling. Okay, after parameterizing and evaluating that model structure, we provide those inputs for different GCM or global climate model realizations that are used to predict the stream flow response, or the Q, the water discharge, water volumetric flow rate, or Q. These water discharge estimates are then run through analysis of extremes techniques. So this analysis of extremes allows us to look at high magnitude flood events that would be projected to occur via the global climate modeling. A little bit more about the methods that we carried out for our global and regional climate models. The climate data sets were publicly available, published results reported in CMIP3 and CMIP5. These are climate modeling projects that are reported internationally, as well as the NARCAP Regional Climate Modeling Project. Simulations were then carried out for the hindcast scenarios, as well as for 74 global climate model simulations that were performed for the forecast period from 2046 to 2065. The hydrologic model that was used was the SWAP model. This was chosen due to its successful past applications in central Kentucky. And the SWAP model relies on topography, soil, and meteorologic data that we utilized. And then we underwent a number of calibration and model evaluation techniques using United States Geological Survey gauge data. That model evaluation was carried out through the SWAT Cup simulation software, and we looked at a number of goodness of fit statistics in order to gain confidence in the quality of our modeling. Okay, we also need to think a little bit about extreme value theory and modeling. This allows us to give the extremes, the flood conditions, such as a 100-year return interval flood event. And so hydrologists have considered a number of methods to try and represent future extreme stream flow. We adopt the extreme value method due to the strong theoretical basis. And so essentially what this method is doing is it's using different approaches to choose what are those extreme events, what are those high magnitude events that we can then look at statistically in our sequences. Okay. And so we really use two approaches. We use the annual maximum approach as well as the peak over threshold approach. And so here we see the peak over threshold approach, which provides additional number of data that gives us the probability distribution for the 220 and 100-year return periods. A little bit about the method. Essentially, we are using this AM and POT method. In the POT method, we're looking at an extremal index as well as a statistical likelihood ratio test in order to move through and understand which of those peak over threshold events are significant. And then in the annual maximum method, well, here we're using the maximum event that occurred each year. And then we're looking at statistical analyses of these tests as well as a likelihood ratio test in order to produce that final distribution via a Gumbel distribution. So results for the South Elkhorn Creek at the United States Geological Survey stream gauge at Fort Springs. Again, this is just for this particular stream where the analysis was carried out, but we do want to look at this case study and think about these results. So first of all, we have results of monthly precipitation and stream flow changes for 2055. And so what we're showing here on the x-axis is just a time series, January, February, March through December. And in the top plot, we have the change in precipitation. The bottom plot, we have a change in stream flow for South Elkhorn Creek. And so here we're seeing in January, February, March, April, we're seeing increased precipitation projected for 2055 from the modeling. Here in February, we see about a 30% increase in precipitation projected. We see pretty flat results for May, June, and July. We see increases in August and September. We see a 10% decrease, that dry time of the year getting drier for October, and then we see increases in precipitation in November and December. Now, on a monthly average basis, we see that stream flow tracks pretty well with the changes in precipitation. So changes in stream flow, again, on the order of 15 to 30% increases in January, February, March, and April, increases in our stream flow, flatter results through May, June, July, increases in August and September, decreases in October, flat in November, and increase in December. Okay, over the entire year, we saw an average annual precipitation and stream flow increasing by about 10 and 11%. So matching up as far as precipitation and stream flow increases. Now, increases in stream flow during flooding is a bit of another story. And so here we see a graph of percentile change on the extreme quantiles and the flood frequency curves. And so here on the x-axis of this bar chart, we see return periods. We see a 2-year event, a 20-year return period event, and a 100-year event. So essentially a 2-year return period. This is a storm event or a flooding event that's expected to happen every 2 years. A 20-year event is expected to happen every 20 years. A 100-year event once every 100 years. And then on the y-axis, here we see the change in the stream flow for this extreme maxima. We see a percent change. We see that the 2-year event is expected to increase by about 25% in 2055. We see the 20-year event is expected to increase by about 35%. We see the 100-year event is expected to increase by about 50%. This means that the 100-year storm event in 2055 is expected to increase by 50%, or that flood event is expected to carry 50% more water discharge, 50% more water peak flow, water flow rate during that event. We also did quite a bit of work looking at uncertainty for different forecast simulations. I think an important point with this graph is just to show that, always that forecast was outpacing the hindcast. And so we're really seeing an increased flood magnitude into the future for South Elkhorn Creek. So results suggest an increase in the average annual precipitation and stream flow by about 10 and 11% for the stream in central Kentucky. Results for future flooding show an increase for the wet region of Kentucky, including about 25, 35, and 50% increases in the 220 and 100-year flood levels. In conclusion today, Kentucky is expected to see increased average annual precipitation in 2055. Kentucky is expected to see increased frequency and magnitude of extreme flooding. The reason is due to higher moisture in the atmosphere, due to warmer atmospheric temperatures, and the expansion of the high pressure subtropical belt within global circulation. The wettest times of the year are projected to get wetter for this region, and the wettest days of the year are projected to get wetter. Using global climate modeling that's projected through hydrologic modeling, we're able to forecast flooding and future extreme flooding. In the case of South Elkhorn Creek, we see that the 100-year flood event in 2055 is projected to transport 50% more water discharge. We're currently working on projects for other streams in eastern and in central Kentucky, and based on our initial findings, we expect to see similar results. And so we're going to keep working in order to understand the forecasted and projected flooding for these regions. Thank you. Thank you very much. This concludes the talk for today, and we'll keep studying and learning about extreme events and flooding in Kentucky. Thank you. Bye-bye.